Hi, everyone. So my name is Gabriel. I'm a computational scientist based in San Francisco, California. I'm the author of a plasma physics package, Plasma JL, a main contributor to a physics-informed neural network package, neural-pde.jl, and I'm a product designer at Substack Inc. here in San Francisco. Today, I want to talk to you about developing battery materials with Python. And in particular, I want to talk about an interesting field of computational physics that I've gotten to know this year. And this is the field of density functional theory, or DFT. DFT tries to solve the problem of determining the properties of matter theoretically. That is, it tries to know what a material that is basically a periodic collection of atoms will do without performing an experiment, going to a lab, or touching matter at all. So purely theoretically. And beyond understanding how it works, today I want to talk to you and look at how DFT can be used to evaluate the performance of materials used in battery electrodes. So how we can do that, so how we can get DFT, apply it to batteries, and do all of that in Python. So why is this interesting? And particularly for a computer science, data science audience, why is this interesting? I think this is an interesting problem because one, it is a tool for understanding matter, which is all around us, and it's very fundamental. Two is that it is a Turing machinist's dream, is what I like to call this, which is it is a part of physics where you can use computers to simulate how actual physical systems behave with high accuracy, which was one of the original goals of computer pioneers. So you can think about the ENIAC computer helping with the Manhattan Project as an example. Another thing is that simply it's useful. It's many fields within physics and engineering and chemistry require understanding and controlling of the properties of matter at the level of individual atoms and molecules for progress. So you can think of batteries, which is the electrochemical cell case. You can think of catalysts, which are these chemical compounds that speed up chemical processes. And you can think of superconductors, which are these very interesting materials that lose their resistance and when their temperature is lowered after to very cold and temperatures. And this field is generally useful enough to have been awarded the Nobel Prize in 1998. So DFT and its development were awarded the Nobel Prize in Chemistry in 1998. And I think most importantly, more knowledge of computer science, software engineering, and data science can help advance the field of density functional theory now more than ever. And we'll talk about that. We'll talk about how machine learning has changed in the field. We'll talk about high throughput density functional theory and the software engineering challenges that it faces. So, maybe I can get one or two of you, at least a little bit interested in the field to look further into it. This talk is for beginners, but it might feel a little daunting or physics-y at points, but I hope it all makes sense at the end. So I'll follow the David Shull's approach to introducing the subject, which I think is pretty clear, and we can sort of take it from there, and I'll be here for questions. So at this point, hopefully you're at least somewhat interested in what DFT is and as a way of understanding matter. But how do we understand matter? How can one know how matter behaves, and how can DFT help? Well, in short, we generally understand matter by using quantum mechanics to get to the electronic structure of a material. And quantum mechanics is an advance of physical theory developed in the 20th century by Niels Bohr, Max Planck, countless others. And it's quite useful. But technically, to determine the behavior of matter, we like the technical description, which we'll start with, and I know it's unintelligible, and we'll slowly chip away at it and make sense of it, is that we're trying to find the ground state or the lowest energy of non-relativistic electrons, basically of electrons, for arbitrary positions of nuclei within the Born-Oppenheimer approximation. It's okay if none of this makes sense yet. I promise you in the next 5 minutes, Probably will. Yeah. So let's talk about the problem statement. So what are we trying to solve here? If you want to understand matter, what is the problem we're trying to solve? So let's imagine a situation where we like to describe the properties of some well-defined collection of atoms. You can think of it as like an isolated molecule for catalyst, or the atoms defining the crystal of an interesting mineral like lithium in our example, right? The fundamental thing we want to know about these atoms is what is their energy and how does their energy change if we move the atoms around. So all we're doing here is accounting for energies at different states and using that to determine properties of something we're interested in. So how do we do that? First of all, we need to find the atom. Where's the atom? So we want to know how the energy of atoms change when we move the atoms around. But to do that, we need to know where the atom is. Simplistically speaking, all we need to know to define where the atom is to define where the nucleus is and where the electrons are in the atom. So what we do is an approximation. So, and we can do that. It's worth pointing out that each proton or neutron in the nucleus has more than 1,800 times the mass of an electron, which means that the nucleus moves much slower than the electrons, which lets us break the problem of defining where the atom is into two parts. The first part is we solve for fixed positions of the atom nuclei the equations that describe the electron motion, and then we account for the nuclei in motion. So the separation of nuclei and electrons into separate mathematical problems is what we call the Born-Oppenheimer approximation, which is exactly what we talked about here. So within the Born-Oppenheimer approximation, we want to know the energy of these electrons while keeping the nuclei constant, and then adding the nuclei motion afterwards. So we want to find the lowest energy of the system in that approximation. So that's the first thing, first part of this. It starts to make a little bit more sense. And once we have the position of the atom, we can start to answer how the energy of the material change as we move the atoms around. So how do we find the energy? Well, in quantum mechanics, we do that by solving the Schrödinger equation, which is, here's the coffee mug version of it, which is basically the Hamiltonian, the wave function is equal to the energy eigenvalue, the wave function. But, this is like the simple version. When we have multiple electrons interacting with multiple nuclei, the equation looks a little bit uglier, which is what you see a little bit below. And not that it matters, but in case you're curious, the terms there mean the kinetic energy, the interaction energy between the electrons and the nuclei, and then the interaction energy between the different electrons. So that's basically the way generally it is done in quantum mechanics. But this approach has several problems. So here's psi, which cannot be found without simultaneously considering the individual electron wave functions associated with all the other electrons. So in other words, Schrödinger's equation is what is called a many-body problem, which is computationally trouble. It's just an extremely difficult computational problem. So for example, if we are interested in a single molecule of, CO2, we have a problem that is 66 dimensional. So 66 dimensional function that you need to solve computationally. So if any of you have done scientific computing, you know that this is like a very high dimensional problem. Basically incredibly impractical. And if we were interested in a nanocluster of 100 platinum atoms, the full wave function requires more than 23,000 dimensions, which is not solvable at all with our current computational structures. It's just not manageable due to this thing called the recursive dimensionality. So if you're trying to compute a scientific computing problem with high dimensions, each dimension makes the problem exponentially more costly. So at the moment that you're at, yeah, more than 10 dimensions is already hard. 23,000 is an understand. It's not feasible at all. And by the way, this is why quantum computers are important, because it would allow us to solve those problems without the approximations we use to solve them right now. But until we have them, what do we do? How is this done? Scientists do know the structure of atoms and know the energy of compounds all the time. So how do we do that? And this is where density functional theory comes in. So the DFT is basically a very smart reformulation of the problem of finding the ground state or lowest state energy, based on the Schrodinger equation. And it basically manages to make the previously impossible a problem manageable. Um, and basically, the reformulation is based on the following theorem, which is the ground state energy from Schrödinger's equation is the unique functional of the electron density. What do I mean by that? This means exactly that there exists a one-to-one mapping between the ground state wave function and the ground state electron density, or basically the electron density of the ground state determines all the properties of the system that you're interested in, which is really good. So why is this important? Is it means that we can think about solving the Schrödinger equation by finding a function of three spatial variables, which is the electron density. What is the density of the electron? X, Y, Z. That's all we need, rather than trying to solve a function that grows exponentially, which is the Schrödinger equation. So for a good example is that for the nanocluster of 100 atoms that we talked about that would need 23,000 dimensions, the DFT would allow for that to be solved with only 3 dimensions, which is a much more solvable situation. And if this loss of dimension confuses you, just for those who know physics, remember that the wave function is not observable. So only the probability density of the wave function is, and that is captured through the DFT approach, which is finding the electron density. But what does this functional look like? We talked about this functional and the F in DFT, the density functional theory. But what does it look like? There's another problem, right? The theorem that we looked at that said that it existed did not say anything about what the functional actually is or what it looks like. It only says it exists. And it has a general form, which you can see on the screen. Basically, we split the functional into the known and the unknown parts of it, and basically we account for kinetic energies and interactions between electrons and nuclei, but we don't actually know what this exactly looks like. So there is a second theorem that helps us, which says that this second theorem says that the electron density that minimizes the energy of the overall functional is a true electron density corresponding to the full solution of the Schrödinger equation. What do I mean by that? Generally, it means that we find a functional by what we call in quantum mechanics the variational principle, which is we pick a trial functional and then we minimize it, which is a computational problem. It's like make an educated guess, pick it, minimize it until it converges, and that is the electron density, and that will give you the energy that you're looking for, which is exactly what the theorem is sort of like hinting at, which is quite useful. Okay, so that was a lot of physics, but it boils down, for a quick recap. This is very esoteric at some points, and thank you for sticking around if you did. It basically, the recap is we figure out how matter behaves through quantum mechanics. By finding the minimal energy of the atoms and how that energy changes, we know how matter behaves. So what we want to do is find the minimal energy of the atoms. We do so by solving Schrödinger's equation for a group of atoms. But solving Schrödinger's equation is hard. It doesn't scale well. It grows exponentially as you have more and more atoms. So it becomes very complicated and not feasible. So we come up with an equivalent formulation of Schrödinger's equation called density functional theory. And this theory says that a 3D functional, so the electron density, three-dimensional, will give us all the information we need to retrieve the ground state energy of a system. And we find that functional by making an initial educated guess of what it is, and then minimizing that function until it converges. And then we can use that to find the energy of the system, which is what we want to be able to determine how matter behaves. But what about batteries, right? If we just looked at a bunch of physics, a bunch of chemistry, how does it say anything about a macro system? How do atoms say anything about the macro system of batteries that we are interested in? Well, electrochemical batteries are basically two electrodes, a cathode and an anode, separated by an electrolyte. And the electrodes are basically compounds, and they can be described very accurately by their crystal structure or atomic structure. And these electrodes, they play a huge role in the performance of a battery. They determine how stable the battery is, determine its power density, its energy density, its equilibrium voltage, its cycling stability, and more. And it turns out that to some approximation, all those properties can be determined from the electronic structure of the molecules that form the electrodes. And thus, they can be determined through DFT, which is amazing. So you start with atoms, and you know the atom structure is something. You use DFT to get their energies, and that itself can help you determine the macro properties of a material that you can use for batteries, which we find fascinating. A simple example of how this can be done is to get the equilibrium voltage of a standard lithium-ion battery. There is a simple approximation that you can see on the screen, which says that the equilibrium voltage is basically equal to the electron voltage is basically equal to the energy post-intercalation minus the energy pre-intercalation minus the energy of lithium divided by a constant and how many electrons changed in this reaction. So basically, you have three energies that you're looking for. So those are three DFT calculations that you can make on in your computer at home. So really cheap calculations that can tell you the equilibrium voltage of a battery you're interested in before you have to go to a lab to build it, before you need to touch anything, without any experimental involvement, can give you a good approximation of what it is, which I find pretty impressive, truly. And how do we do that in Python? So in Python, there are several packages for DFT, a lot of them in languages that are older than me. But in Python, we can do that with ASC and GPOT, which are very interesting and good packages. And I'll just walk you through a bit of a code of what that would look like, and we can just do line by line. So we import from ASC the atom structures. From GPOT, we import the calculators. We give it a name. And in line 5, we determine a parameter. None of this is like very interesting, but around line 8, it gets quite interesting, which is we make a lithium structure. So where we set an atom, a lithium atom, we define its cell, so its crystal structure to look like so. So you basically define a matrix to say where the lithium atoms are. And then you say that this is a periodic boundary condition, so this will repeat itself. Around line 15, we set up a DFT calculator. So it's like we have the structure, Now I want to calculate the energy of the structure. So I set up a calculator in line 17, 18, 19. You don't need to worry about what the cutoffs and so on mean yet. And then I attach this calculator to the bulk in line 20. And then basically what I do is I get the potential energy, which is the energy we're looking for in line 23, and then I print it. And that's it. With those 25 lines of code, I can determine the energy of lithium that you see here on the right, which is quite fascinating, I find. We can do a bit of a live demo. Let's see here. So this is my workstation of, let me zoom in for you. So this is my workstation of a battery system I was working on in the summer, which is a lithium oxide battery system. And in this world, you can see that I set a few compounds here. So I define them. I have some corrections. This is a bit more advanced. This is like production code. But I get their potential energies very simply here. And then I use that potential energy to get different values or different things I'm interested in, and then get aspects of the battery system. So its energy density, its volumetric energy density, its specific capacity. And then I can also get the electronic structure of the compounds I'm interested in and generate those graphs that you see here on the right, which are quite cool. Yeah, so let me go back to presenting. Thank you. You can email me at this address if you want to talk. If you can follow me on Twitter if you want to stay in touch. But beyond that, I really appreciate your time, and I'll take questions now.
Oh, thank you very much for your talk today. I'll give everyone a couple of seconds to put in their questions because we've got plenty of time. And I've got a little question. So what originally got you into data science and programming?
I've been doing that since I was 17 or 16. What got me into data science for scientific computing was a numerical analysis class I took in college. I thought it was just fascinating that we could use computers to solve really hard mathematical problems, and not just toy problems that you can do it with pencil and paper. So sort of seeing the capability of computers and understanding reality around us got me into data science.
Oh, cool. Excellent. And here's our first question from Mila. What is the system size you're working with? How does the calculation speed scale with the system size?
The system size, that we work on with batteries is like at the worst case scenario, they're at the nanoscale. So it's a few hundred atoms at the worst case scenario. And the calculation speed at the worst case scenario is already pretty high. So most of what supercomputers do actually is DFT calculations. It's a big chunk, a big percentage of their workload. So it's a lot of chemists running these calculations. But for small systems of like 10 atoms or so, you can run them in like 20 minutes in your computer at home. So you have the ranges of like, I can do some simple stuff and approximations with at home, just on my computer. And then if I want to understand nanoclusters, then I probably need a supercomputer.